Okay, first off, I'm sorry that I can't be here today. I had a meeting that I totally had forgotten about. Um, so what we're going to learn about today are scattergrams and correlation and linear regressions. Let's start with scatterplots. Scatterplots are just a series of points. And what can we really tell about each of these plots? Well, the first one is the amount of sunlight versus breast cancer deaths. So if we notice there's a whole bunch of cities and how much sunlight they receive and the number of deaths related to breast cancer. So you can tell that as the amount of sunlight increases, the number of deaths decreases. But is that really causation? Is the sunlight actually preventing the deaths? Or is there something else there? Well, one thing you can think about is in these cities that have more sunlight every year, what could be the causes that make this number of deaths decrease? Could it be things like they're more active, they're getting more exercise, they're outside more? So when you're looking at a graph and you're talking about a correlation between the variables, we can notice that there's a pattern. But I want you to always keep in the back of your mind that just because there's a correlation, it doesn't necessarily mean there's a causation. So what do we notice here about the military draft notices versus birthdays? Is there any kind of correlation there? Doesn't look like it. It looks like it's very, very random. So it seems that there is no correlation between birthday and draft notice. But let's look at the last one. This one is age and height. Does there seem to be a correlation there? As age increases, height increases. Now it does seem like that's that one could be a causation, but look at the ages and look at the heights. What if we had had more points? Would there be a difference? So that's the type of things you want to talk about if you're looking at your data in a scatter plot. Now, the scatter plot can show, as we were talking about, a relationship or association between the two variables. And they're identified by their direction, positive or negative, and their strength, strong or weak. So look at this first diagram. Since it's going up, as we increase this way, we increase this way. So this would be a positive. Would you consider this one strong? I would. I would consider this one a strong positive. Well, what about these others? Well, this one's still positive, but notice how the points are very, very diverse. They're separated. This would be considered a weak positive. What about here? Do you see any kind of pattern? I would say this one is no correlation. And our last one, the next one, we're going down, so it's a negative. But again, like this one, the pattern is very spread out. So this one would be a weak negative. And our last one will be a strong negative. Again, just because we see a pattern or relationship, it does not imply causation. It's just showing that there's a trend in one direction or the other. So make sure when you're looking at your own data, you think about causation versus just seeing a correlation. There's two different things. Now, IB does expect a few things from you, that you are able to draw a scattergram from the data, find the mean and standard deviation of the data, and draw a line of best fit through the mean and predict an outcome from what you've drawn. So let's look at the first example. See if I can zoom out a little bit here. There we go. 8 students in Mr. O'Neill's physical education class did push-ups. Here's the number of push-ups. And sit-ups. And here's the number of sit-ups. And we have them in the table. The graph to the right shows the results of the first 7 students. What kind of correlation does the data show? Well, it looks like there is a pattern, right? It looks like it could possibly be a strong positive. What does this imply about the relationship between push-ups and sit-ups? Does it imply that the more push-ups you can do, the more sit-ups you can do? But is it because of the number of push-ups you did that you can do more sit-ups? That's the difference between a correlation and a causation. Now plot the results for the 8th student on the graph. So the 8th student, here's the student numbers, is 2552. So here's 20, 25, and here's 52. Now what has happened? Plotting that 8th student really did make it a little bit more spread out. Sorry. So the next thing we need to do is find the mean point of the data. Now the mean point is the mean of our x's and the mean of our y's. One way we can do this is by literally adding up all your x values and dividing by 8, and adding up your y values and dividing by y. But for what we're doing in class here, we can do that in the calculator as well. So let's review how to put data in the calculator. Now this time, we actually have an x and a y value. So when we go into our calculator, we're going to put the x values in L1 and the y values in L2. So remember, to put in those values, we're going to go to Stat, Edit, and then clear out anything that we have under our values. So L1 is going to be the number of push-ups. And then in L2, we're going to put the number of sit-ups. If we need to pause the video here while people get the calculators set up, that would be fine. Once you have your data entered, we're going to go to Stat. Now remember, before we had one variable. Now sometimes we had a frequency list that we might put in L2, but this time it's two different variables, L1 and L2. So to find the mean, we're going to go to Stat, and then arrow over to the Calc menu. And since this is two variables, we're going to go to two variable stats. And let's talk about some of the things we see here. So when we arrow over to Calc, we can go down to two variable statistics and press Enter. It asks us if our X values are in L1 and our Y values are in L2. Notice that we could also have a frequency list here. We don't. So when we hit Calculate, it's going to give us a whole bunch of stuff. Right now, we're only actually looking for our mean of the X's and the mean of the Y's. But sometimes we might want our standard deviation as well, which is this, remember the circle with the hat on it, that lowercase sigma. So let's write down the stuff that we're going to need for this. Right now, we're just looking for X bar and Y bar. We're looking for the mean of our X's, which is 34, and the mean of our Y's. Well, I don't see it right now, but notice the down arrow means to go down. Oh, there it is. Y bar is 40. So the mean of our X's is 34, and the mean of our Y's is 40. So let's plot that point. 34 and 40 is our mean value, and it says to name that point X. And we're going to draw a line of best fit. Now, a line of best fit goes through the majority of our points. It may not go through all of them, but it's following the pattern. So we want to always go through our mean point, that X bar, Y bar. Now, I could go through that bar this way. Is that going to? No, we said it was positive. So we want it to go up. Would that be here? No. Notice that the majority of the points would go this way. So you want to try to hit as many points as you can. And there's my line of best fit. You can use a line of best fit to make predictions. Now, it doesn't always come true because we have these points that are off of that line. But the prediction we can make is if a student can do 60 push-ups, how many sit-ups can they do? Well, you could use the line and go to where 60 is. And then follow back. And it would be 60 sit-ups. Let's try another one. In practice B, we have a vertical spring, and it's stretched by hanging different weights on its lower end. Here's the weights, and here's the length of the string when it was measured. Now you're asked to plot the points on a scatter diagram, but right now let's just practice plugging this in the calculator and finding our mean standard deviation for both X and Y. So we go into Stat, Edit, and remember you can go up to the L2 and hit Clear and clear out your list. Don't hit Delete, but Clear. And we can type in our values for our X's, and we can type in the values for our Y's. Once you have all of your x values and your y values entered, we're going to go to two variable stats. So hit stat, calculate, and this is two variables, an x and a y. So you're going to get a whole bunch of data. Remember that we're looking for our mean of our load, which would be the weight. That's x bar. And that's 4, but let's think about what it was representing. That's 4 kilograms. And what's the standard deviation of our x's? Well, that's that symbol. That's going to be 2.58 kilograms. And thinking back on when we talked about normal distribution, remember that's telling us their average is 4, give or take 2.58. We also want to write down our y bar, which is the average of our y's. And our y's were representing length of that string, and it was measured in centimeters. We also want to write down the standard deviation of our y's, which is a little bit lower. There it is, 4.778, so that would be 4.78 centimeters. So I'm assuming you could plot the points, plot that mean point, x bar, y bar, and draw a line of best fit. Remember, your line of best fit is going to hit the majority of your points. Now, we've been talking about correlation and sketching that line of best fit. But there's also something else we can do to be a little bit more precise when we're talking about it. Your calculator can give you something called Pearson's product moment correlation coefficient. It's designated by an R. This diagram shows patterns that would have certain R values. Notice that when we have a 1, it's positive, and the points are really, really, really close together. It's almost like they're in a perfect line. When we get to -1, again, they're really, really close together, but they're going down. What happens when it's 0? Well, yeah, it's all over the place. There is no correlation whatsoever. And I want to use a little bit of a different If it was exactly 1, that indicates a perfect positive. What do you think if it was 0.8? Or really anything, let's just say over 0.75. That's going to be a strong positive. If we have a value between 0.25 actually, let me change that. What if we have a value between 0.5 and 0.75? So somewhere between the 0.4 and 0.8. That's actually considered a moderate positive. If it was between 0.25 and 0.5, so that would be where the 0.4 runs into, we would consider that a weak positive. And if we had a correlation of close to 0, so really, really low, below 0.25, that would be considered a very weak positive. Now, all of these, the numbers would be the same, but if it was negative, we'd be saying negative instead. So a -1 would be perfect negative. Around a 0.8 would be a strong negative. Between -0.5 and -0.75, you're going to have a moderate. So we're just going to be describing it in certain ways. Now, there are formulas for this, and we will be going over how to find this coefficient by hand. But for what we're doing right now, just the introduction, we're going to use the calculator. So, to make sure our calculator will give us this correlation coefficient, we have to turn our diagnostics on. So there's a couple of ways to do it. Here's one way, which is going through the catalog. On our calculators, if you have an 84 plus, you can go all the way down under mode. I'm sorry, I forgot to show you what I pressed. I pressed mode. And if we go all the way down to the next page, stat diagnostics need to be on. So if we go down, here's stat diagnostics. We want them on. What this does is it tells the calculator that we want it to find R for us. So make sure in mode, you go all the way down to the second screen and turn on stat diagnostics. We want it to be on. And now let's look at data again. We're going to look back at Mr. O'Neill's physical education class again. And we looked at that just a moment ago. So we want to clear out this other data. Actually, no, I already did it. I was going to say we can actually, since we already had the second one in there, that spring, let's just use that, sorry. So if you already cleared it out like me, you can clear it out, or I'm going to type it back in. Sorry. So we've got that spring and the weight again. So the way we're going to find this is we're going to go to stat again. So let's write it down. We're going to go to stat. Then we're going to arrow over to calc. And we're actually going to do a linear regression. What that's doing is finding that line of best fit for us. So it's for L-I-N-R-E-G. And notice it says that it's going to put it in the form AX plus B. It makes sure where our X values are and our Y values are. You can put in a frequency list. There's even a place where you can store this equation if you needed to use it again. We're not going to be using it again. So we're just going to go down to calculate. And it gives me a whole bunch of stuff. Let me write down everything it gives me. A equals 1.825. B is 22.7. R squared is 0.9724. I'm just going to stop there. R is 0.986. So which one is the Pearson's product moment correlation coefficient? It's R. So how would you describe it? Well, it's positive, and it is really, really strong. So this is a strong positive correlation. It's above 0.8. It is almost 1. This is a strong positive correlation. We can even write down the equation of the regression line. Notice that A in the calculator is in front of X. That's sort of like our M. And since it did give me exact, I'm going to leave that as an exact number. And it says make sure you indicate what X and Y stand for. X is the load in kilograms, and Y is the length in centimeters. Use your equation to predict how long the spring will stretch with a load of 10 kilograms. Remember, load is our X, so we're going to let X be 10. So you're literally going to plug in 10 for your X. Notice I'm showing that step to get method points. And you should get, oh, if I typed it in right, times 10 plus 22.7, you should get 40.95. Don't forget your units. That's centimeters. You can also use the equation to predict how much mass or weight is needed to stretch the spring a certain distance. So if we have a certain length, that's going to be a Y value of 30. Notice I showed plugging it in the equation, so I get my method point. IB doesn't care about seeing every single one of your steps, but they do want to see that. And hopefully, when you solve it, you get the same thing I did, and I get X equals 4 kilograms. Sorry about the pause there. I was double checking what was going to actually be tested this year, and we're going to kind of skip over. So if you can skip with me over to example D. A shopkeeper wanted to investigate whether or not there was a correlation between the prices of food in 1992 and 2002. Now we have 8 pieces of data, which usually isn't enough to do much, but it's enough for us to practice here. So we want to find the mean and standard deviation of the prices, and we're going to ignore this right now. We're just going to practice using the calculator to calculate everything. Now, if you are choosing to do a linear regression for your project, you will be having to do some stuff by hand. But we're going to talk about that on Friday, later. So we're going to type in the 1992 prices into our X. And the 2002 prices into the Y values. Now remember, to find the mean and standard deviation, we're going to go to Stat, and that's under the 2 variable statistics. So we'll make a note that to find these, again, that's under 2 variable stats. So if you press enter and go all these down to calculate, hopefully you'll get the same mean and you choose the right standard deviation. And for the Y's, and the right standard deviation. Now it asks us to find the correlation coefficient. That's R. So to find R, that's not under two variable stats. That's under the linear regression. So you're going to go back to stat, go over to calculate, and go down for a linear regression. The R value you get should be 0.672. Notice it's a positive correlation, but is this one really strong? I consider this one a moderate positive correlation. Also, from the screen that you have, you should be able to write your line of best fit. Now, from your line of best fit, can we find out what we would expect to pay in 2002 for an item costing $2.60 in 1992? Now let's think about, again, which one was our X and which one was our Y. X was the 1992 price, and Y was the 2002 price. So if we're trying to find the 2002 price, we're going to plug in $2.60 in for X. And we should get $2.58. Now, E is a great question. Is there an item you would omit to increase the correlation coefficient? Is there one that's preventing this from being a good pattern? So let's take a look at all of them. We're increasing. Ooh, what about coffee? The coffee has actually gone down in price over the years. So wouldn't that be one that kind of changes our line of best fit? So I would say coffee. Because the price has gone down since 1992. Let's see if we have another example that would be a good one. We already did the one with the weights at the end. So, as your homework, you will be getting a sheet that has some data, and you will be expected to find that line of best fit and answer some questions about it.